All right, so we are starting a unit on Newton's laws, and today we're going to go ahead and take a look at Newton's first law of motion. But before we do that, we're just going to take a quick reminder of vector diagrams, and we want to do this because as we start talking about Newton's second law, sort of the mathematical side of Newton's laws of motion, then it's going to be important for us to remember our vector diagrams. So let's dig in. We're going to start by going to this website right here. We're going to go ahead and jump onto that website. And this is just a short reading of vector diagrams. And what we want to remember about vector diagrams is that they show us magnitude and the direction of motion. So if I'm looking at these arrows, I can see that all of these arrows are the same size and they are all going in the same direction. So what this tells me is that I have velocities that are all the same. Okay. Now, if I come down a little farther, what I have here, it shows the difference between vector diagrams where our velocity is constant, meaning the same from one moment in time to the next. And if we look at this next diagram, we can see that our vectors are increasing in size or magnitude. And this tells us that we're looking at something that's accelerating. So my vector is larger in the next second, and larger still, and larger and larger. And so this shows us an object that is accelerating. The last thing that we're looking at is just showing us how vector diagrams can also show us the direction of forces as well as acceleration. So for instance, if I'm throwing a ball in the air and it starts to move up and then down, the A here is for acceleration, and so what it's telling us is that that's the direction of acceleration as the ball moves to the top and then moves back down towards the ground, because acceleration, as we throw the ball up, it goes up and then it starts to slow down, and as a result the acceleration goes with it. So again, just doing a quick review so that we remember that when we're talking about vector diagrams, that it has to do with the size and the magnitude of the arrow. All right, so with that said, let's go ahead and hop back into our notes here. And what this little animation shows us, this little animation is showing us that if we have a ball rolling down a track, that it gives us the directions of both velocity and acceleration as it first moves down the track, then starts to slow down, then changes direction, and then slows down even further. Now, like I said, I don't want to spend too much time talking about this. I really just wanted to just kind of help us remember what those arrows mean when we're talking about force diagrams, which is what we're going to be doing next week. All right, so let's talk about ideas of motion before Isaac Newton. So before Isaac Newton, scientists thought of motion in terms of it always having to be a force applied to it. So if we look at our text here, it basically said that prior to Galileo and Newton, people believed that in order for any motion to take place, that a force would always have to be applied to that object. They thought it was a natural tendency of objects to always come to rest. And if we roll a ball here on Earth, that's kind of the way it works, because you roll, and then after a while, forces will get a hold of it, and the ball will stop. So scientists thought that that was the nature of all motion. And it wasn't until Galileo started to sort of think differently that we started to know and have some different ideas about motion. All right, so let's talk about what Galileo figured out. Well, what he did is he used a lot of incline ramps, and he would roll balls around those ramps, and he would observe their motion. For instance, at one point, he constructed a little U-shaped ramp, and he noticed that when he rolled the ball down the ramp, that it would not roll back as high. So it would roll to about here, and then it would roll back to about here, and then about here, and then finally it would stop. And what he figured out was that there was more than one force working on the ball, and as a result of that, the ball was not able to achieve its original height. So what Galileo guessed was that he guessed that if you could take away friction, which is a force, if you could take away friction and any force working on a ball like that, that it would be able to achieve its original height. Then he went on to figure out that if you tilted the ramp down a little bit, so taking the ramp from here and tilting it down like in figure B, that you would have to have more distance between here and here in order to achieve that same height. So then he went on to think about, well, what would happen if you completely, in an environment where there was no friction, what would happen if you completely flattened the incline? Well, what would happen, according to Galileo, in a frictionless environment, he said that this ball would just keep moving forever. So what he said is that if there's no forces acting on a moving object, that object would not eventually come to rest as scientists previously thought. In fact, it would just keep moving, kind of like this. What you're going to see here. So that's a clip from the movie Gravity. And in that scene, Dr. Stone is thrown from her, she's attached to the space shuttle, she's thrown from the space shuttle. And because space is frictionless, when she achieves that velocity in a frictionless environment, if another force doesn't stop her, she would just keep tumbling and tumbling and tumbling into space. Fortunately, George Clooney's character comes along and saves her. He's the opposing force that keeps her from tumbling out to space. It's pretty cool. All right, so that brings us to Newton and his 3 laws. So Isaac Newton lived pretty much after Galileo. He started thinking about and proposing his laws in the mid to late 1600s. He built on the work of Galileo and others, and his laws are essentially the foundation for mechanics. So we have a lot to thank Isaac Newton and Galileo for. Thanks, guys. All right, let's talk Newton's first law of motion, because that's what we're talking about. Right, this is what the law states. It states an object moving at a constant or a speed that doesn't change will continue at that speed without an additional force being applied. So what that means is that an object that's in motion will stay in motion unless another force acts upon it, and an object will stay at rest unless, again, another force acts upon it. So let's take a look at our little guy down here on his skateboard. What we see is that the skateboard moves along until something stops its motion. In this case, it's this rock. But what's interesting here is that the little guy on top of it keeps going. So what we're trying to figure out is, even though the skateboard stops, why does he keep going? What force is now acting upon him that's pulling him off the skateboard? Well, what's happening here is that the little guy on the skateboard here is actually has something that we call inertia. All right, let's talk about inertia. All right, inertia, by definition, is the tendency of any object to resist any change in its motion. In other words, objects would prefer just to do what they're currently doing. So if you have an object at rest, it's going to stay at rest. If you have an object that's in motion, it's going to stay in motion, and that's called inertia. So if we look back at our little guy on the skateboard here, he is not a part of the skateboard. He's on the skateboard, but he's not a part of the skateboard. When the skateboard stops, his inertia keeps carrying him forward. Eventually, gravity gets a hold of him and pulls him down to the ground. Gravity, which is a force, then acts upon this little guy and pulls him down to the ground. All right, so let's talk about inertia. Again, it's the tendency of any object to resist change in motion. So one thing you want to remember about inertia is that as the mass of an object increases, its inertia increases. So what that really means, it just means that bigger objects have more inertia. So for instance, if I'm looking at these 2 objects here, I have a boulder and I have a lawnmower. So the question is, which has more inertia, the boulder or the lawnmower? If you said the boulder, you were right, and it's because the boulder has significantly more mass. Now let's think about it. Which object then would require more force to move it? Right again. You would need more force to move this boulder than you would this lawnmower. So what we understand is that objects with more inertia require more force to move them. All right, so here's a couple of questions to consider. The first is, how is inertia related to mass? Well, we kind of just answered that a second ago when we said the greater the mass of an object, the more inertia it has. Another question that we want to ask is, what does inertia have to do with Newton's first law? Let's think about that for a second, but just a second. Okay. Because remember, we're going to talk about all three laws. And if we're talking about Newton's first law, that one really talks about our observations. So what does inertia have to do with Newton's first law? Well, Newton speaks to objects wanting to stay at rest or wanting to be in motion until another force acts upon the object. The inertia of that object is the clue as to how much force we're going to need to either start something or stop something. So inertia, Newton's first law of motion, is actually also called his law of inertia, which basically says however much mass you have is going to be related to how much force we're going to need in order to move you. All right. So let's look at some practical applications of inertia. And what I'd like you to do here is in your notebook, I want you to look at the animation and I want you to answer these two questions. Okay? That's your assignment for today. Now notice what's happening here. The car is hitting the wall and the driver flies out of the car. So here's one question to consider. Using the term inertia, can you explain why the driver flies out of the car? Okay, that's one question I want you to try and answer. So at any point you can stop the video and answer that. And the second question that I'd like you to answer is explain why wearing a seatbelt would keep the driver in the car. Okay, so those are two questions I'd like you to answer. And when you get back, I would love to go ahead and read what you've written for these. Okay, and again, remember, the driver is not actually part of the car, and so even though the car stops, the driver isn't going to necessarily stop. Okay, have a great day.